I wanted to make another video concerning how I'm going to be optimizing the thermistor circuit for the 3D printer filament maker. So right here we have the circuit. It's just going to be powered by the 3.3 volts, which is on the microcontroller. We're going to have a set resistor, and then we're going to have the thermistor. So in the previous video, I set the set resistor as 1 kilo ohms, but I kind of just did that randomly. I did it like, I just chose it because it was a good value to choose for then. But now I actually go into the math and talk about what should be chosen for this and how I'm getting these values. So first of all, the ADC voltage is going to be the same thing as the thermistor voltage because we have the circuit set up like this. I believe this is flip-flopped from the previous video, but this just makes the math a little bit easier. The resistance of the thermistor is going to be found by the voltage of the thermistor over the current through the thermistor. So the current's going to be the current and the R set as well, because they're in series. It's the same thing. So it's going to be the 3.3 minus the VADC over the resistance of the set resistor, and that's just going to determine the resistance. From there we can just simply use our table here just to figure out what the temperature is from the resistance. And then we're going to be using 12-bit ADC from my implementation. That's the highest one I could get. I know that Arduinos have 10-bit, I think. Maybe other microcontrollers have a little bit better, but yeah. So the properties for the thermistor I found using this table, just going to be 125 kilo ohms at 20 C, which is about room temperature. It's a little cold, but it's about then. And then I'm just guessing that we're going to be melting the PET from 180 to 240, somewhere within that range. So I'm going to pick the optimal resistor for our set based on that. So at 180 C, it's going to be 90 ohms. So you can just scroll down the table and go to 180, which is right here. It's about 900. And then at 240, it's about 300. So you just use the same table again. 240, which is somewhere, yeah, about 300-ish. Not being exact, because this doesn't really matter. Just giving a decent range. So using these two, we have a couple choices about how to pick our resistor. So one is just sticking with the 1K. That's kind of too easy. It's not going to give us a very accurate reading as we tend towards the higher temperatures, because as you see here, the lower temperatures change a lot. So if you're going from 20 C, which is about 125, to 30 C, it actually changes by about 50 kilo ohms, which is a lot. Whereas if you go down to, so that was just a 10-degree change. If you go down to 200 C to 210 C, it's only changing 100 ohms, from 582 to 483. So there's a big difference there. And our other choice is to optimize the whole ADC range. So like the usable range, I guess, which is going to be 20 C to 240 C. And our third option is going to be optimize the printing temperatures from 180 C to 240 C, which is what I'm going to be doing because I don't really care about room temperature. I care being most accurate when I get to this range up here. So firstly, I'm going to go into how we would optimize this using the whole ADC range of 20 C to 240 C. I wrote it up in Desmos just because I feel like that's the easiest way to understand. So right here, Y equals 3.3. I'm just creating a voltage divider where this is the thermistor voltage right here. So this case where it's 125 kilo ohms is when it's room temperature about 20 C. So when you enable this, you can see the output voltage based on whatever R set you pick. As well, when you enable this one, this is for 300, so this is the resistance for the 240 C. So you kind of notice something this is going to be the top value we would ever get for any R set, and this is going to be the bottom value we would ever get for any R set, because this is theoretically the maximum and minimum that the R thermistor would ever be. So to pick the optimal R set resistor, you would want to pick whatever one has the largest range here, because you don't want to pick this value over here, because this value actually leaves out all of this ADC range here. But you do want to pick a value in here because it has a larger ADC range that would be input to the microcontroller. So I'm going to enable this, which is just the subtraction between these two. You can see that it's just doing a simple subtraction of this top one minus this bottom one. And then just to get this equation here. So this is useful in the sense that you can actually see, dependent on the R set, what kind of voltage range you would get for the ADC. So it's not going to tell you like the minimum or the maximum, it's just going to tell you the magnitude, like how many volts out of the 3.3 is going to be being received by the ADC. So here is about 2.992 volts out of the 3.3. So if we choose this around 6.1K, we're actually getting about 90.66% of the ADC usable range, which is pretty good. This value is wrong. I did a different calculation earlier, but this is actually a pretty good range here. We're almost at using 100 for the temperatures of 20 to 240C. However, when you consider the temperatures from 180 to 240C, which are kind of the more important temperatures because this is where you're actually melting the PET plastic, you actually are only using 8.17%, because now instead of this top temperature being 125K, it's actually only 900K, which is what we found as the around the lowest printing temperature. So you're really only using you're really only using 8.169%. So this isn't going to be the best choice for the 180 to 240, but it will be the best choice for the 20 to 240. So if you really care about monitoring the room temperature all the way up until the printing temperature, then yeah, this is the best. But I don't really care, because the temperature that I care about monitoring is when the heater is going to be on and the filament is going through it. This whole thing, why this percent is different from this percent, this whole matters because this thermistor is nonlinear. So as the temperature decreases, the resistance doesn't decrease in a linear fashion with it. So we're going to find that choosing the R set for these two different optimizations is going to be different. So the resistor from 20C to 240C is going to be different from 180C to 240C. So now we can move on to looking at the optimal resistor for the 100 ADC to 240C. So we saw here that 6.1K was the optimal for this. We found it using this equation. I'm basically going to do the same thing, just substituting in the different numbers. So you can see here that this is the 900, which corresponds to the lowest printing temperature, and then this is the 300, which corresponds to the higher printing temperature. So you can note that there's a much smaller range as compared to this one, but that is purely due to the fact that we are having a much smaller temperature range as well. So now we can plot the differences, which gives us the magnitude of the ADC given, and we can find the maximum value here. So we're only going to be using about 0.884 volts out of the 3.3 volts, which is not great. However, it is better than the previous one, where we were only using around 8% of that. So overall, for the 20 to 240C, we can plug in our, so we chose 500 for this, 500 ohms. So plugging in the 125K and the 300K, which is the range for the room temperature to the highest temperature, we can see that it's not better than the other one, it's actually worse overall. So we only use up about 62% of the ADC range, whereas the other one uses up 96.6%. However, for the 180C to the 240C, we can see that we're using actually 26.7857%. So it's actually about 3 times larger than the other one, which is actually more important because we're going to be using this temperature range more than the others. So it really, when 20C to 180C, that really only matters when it's heating up, but when you're using it, which is the most important part to keep track of the temperature ranges, it's actually more important to have a wider range there, because then it can increment and decrement by a smaller value. So this is actually going to be not great when you're looking at smaller temperatures, because if you choose a really low resistor like 500 and then you have, let's say, 125K, when it jumps from here, that's 6K difference. So the voltage is going to change quite a bit when you look at the ADC value, so your temperature isn't going to be very precise. However, when you get all the way down to, like, let's say, when you get all the way down to 200, this is going to be what's changing a lot, because this is about 580 and 570, which is quite a bit around the 500 resistor that we chose. So this will actually make a larger change on that resistor, which can give us a more accurate reading. So going back to here, we can see that choosing a different temperature range that we want can give us a better idea of what resistor we should choose for our circuit for the R set. If we choose a larger range like this, we should choose an appropriate resistor, but if we really just care about the smaller ranges, we should choose this smaller resistor here. I'm going to be actually implementing a 500 because it's just going to be 2 1Ks in parallel, which is going to be fairly easy just to implement. There are other options for this, such as increasing the ADC range by having a larger input voltage. So we're kind of limited by this 3.3 here, and I don't really want to fry the ADC input, but you could have a 5-volt input and let this voltage divider go from like the full range of like 0 to 3.3, and then after that you might not care what it's going to if you set your equation up like that. But the one thing you would need to watch out for is that our thermistor might get so large to the point where the 5 volts could enter the ADC, and for that you would want to have a Zener diode of 3.3 volts or some other circuit protection system that would protect the ADC and let all the current go through instead of climbing up the voltage so that the ADC wouldn't reach 5 volts. So that's all I wanted to talk about and specify about how I'm choosing this R set for my temperature optimization for the printing temperatures. I'm going to be going with, as I said, the 500 ohm, but I just wanted to make a video about how I'm doing this math to figure out what's going on here and what I should choose. I also wanted to point out that you can make circuit diagrams of this to also see what's going on. So I've plotted the 1K, 6.1K, and 500. So this was the original resistor that we picked just out of just guessing, just randomly picking one. This was the best resistor for the 20C to 240C, and this was the best resistor for the 180C to the 240C. Then I have set up 20C, 180C, and 240C. So the 20C is just going to be the 125K as the thermistor, the 180C is going to be the 900, 240 is the 300, and this is just given from the data sheet here. So if you go back to this thing and just look up the temperature, you'll find the same resistance around that. So first I'm just going to be plotting the 1K. So 1K goes at 20C, it's about 3.3, which is pretty good because it's at the top of the range. Once we hit 240C, we notice that it goes around 0.7-ish K. I'm just going to make this 0 to make it better to see. And then when we plot one ADC, we notice that it as well is around the middle, which is pretty good. However, we can see that this range right here, it only makes up a portion of the entire ADC range that we are given here. And then moving on to the 6.1K, I'm going to click this one right here. So we'll see that we don't go as high on the top, and we go a lot lower down than the previous one. So in comparison to the 1K, so the 6.1K is the blue and the green, and then I'm going to click this. So the 1K is a little bit higher than that, but it's also a lot higher than this bottom one. So we can note that the 6.1K has a wider range of usable ADC values because it's actually going to be using from around 0.15 volts to 3.15 volts. So it doesn't go as high as the 1K, but it does have a wider range. So this is just a visual representation of why it's a better choice than the 1K for the whole 20C to 240C. So now I'm going to select the 6.1K for the whole range, and then we're going to go to the 500. So the 500 was the best between 180 and 240, but if you look at this comparing to the 20 to 240, you can see that it starts off really high. So the 500 has a very high starting voltage and a much higher ending voltage compared to the 6.1K. So the usable range from this is only about 3.3 volts to 1.2 volts, around that, whereas the 6.1K has a much larger ADC range. However, if you look at the range from 180C on the 6.1K, it's only in the range of millivolts, but if you look at the range of the 500, you can actually see that it is a lot more. So this is the 6.1K right here, and then this is the 500K. So you can see that it's almost 3 times larger in width than the 6.1K. So we're going to be getting 3 times more resolution rather than using the 6.1K. So thus we can conclude that using the 500 ohm resistor is going to give us a better resolution than the 6.1K would for the range of 180C to 240C. So that pretty much concludes everything. I just want to make this video to inform people about how I'm making the decisions on which resistors to use. I'm just using these equations, using this data sheet, and then just a little bit of math to figure it out, and then some LT splice to just visualize it. So thanks for watching. Have a good day.